So tonight I'm going to show you three things. Two will be probably useful tips that you can use, and one I'll just show it because it's cool. So I'm going to start with the curiosity. Do you know that JPEG images don't store pixels? There's not a single pixel in the file. What JPEG store are frequency coefficients, which I'm going to explain in a minute. And all that weird way of storing data is dictated by our eyes. Our eyes are quite imperfect. So, for example, if we take an image and blur it, then you can still see that's about the same image. You can still recognize it. People in the back probably didn't even notice any difference. But by blurring it, I've actually removed a lot of data from the image. And on the right here, that's the part that's been removed. Now, with your eyes, with your squishy brain, you see on the left, that's the image, and on the right is just like some squiggly edges, doesn't really look that important. But if you asked a robot, a machine that analyzes amount of entropy, amount of information in the picture, it would tell you that the one on the left is just 2% of the information, and the one on the right is 98% of information. So now you can see with your own eyes how little information in the images you see. So if we can get rid of that bulk of unimportant detail from the image, we can greatly reduce amount of data that we need to store. And that's what JPEG does. First, it divides the image into 8x8 blocks because it just happens to be mathematically much easier to work with. Because each block contains 64 pixels, and here magical math comes in. 64 pixels can form 64 different frequencies. These frequencies, if you interpret them visually, they form different patterns. It's very similar to analyzing frequencies of audio. When you have a music and you sample a waveform of music, it gives you some kind of a squiggly line. But you can analyze that this piece of music has some bass, some treble noises, the different frequencies. The visual interpretation of this is if you take the intensive amplitude, it's brighter pixel. If you take the lower ones, it's the dark pixel. And the frequency squeezed into a box gives you a pattern. So all those 64 different patterns can be combined together in different proportions to form any shape within that block. It's mathematically beautiful. It's visually hard to show that it really works. But imagine like you had a 64 layers in Photoshop with some additive blending. And if you removed some of the layers and put them back, that would give you a certain image. Depending on combination of those layers, you could achieve any image. And here's the thing with your eyes. Your eyes are sensitive to lower frequencies. Some of the patterns are important, like these are super important. The ones at the end are higher frequencies, are smaller details, are more seen as noise. So what JPEG does is it can remove the less important ones. When you save an image with certain quality, you have a quality slider, and the lower quality you get, the more of those frequencies you remove. That's a huge reduction because most of them are not visible to your eyes. Not all of them are in any image. If you have a flatter piece of image, like a sky, it's only going to contain the few of those lower frequency gradienty ones and not the noisy ones to begin with. So this is the key behind the great compression you get in JPEG, because you use few coefficients to represent those few patterns, but they still form the full 64 pixels of the block. And there's more. Now, if we put back the JPEG into those blocks, typically they're laid out in the file left to right, top to bottom. So when your image loads, it will also load in the same order as all of your data in your file. If you've worked with poorly compressed images on your websites, you've seen this a lot of time. It just goes and goes and goes and goes and goes. We can do better than that without adding any extra cost to the file, just by using the JPEG technology that we already have. Instead of putting all of the frequencies for every block in the file in a group, we rearrange them and put those important ones, the ones that form background colors and very rough edges of the images, we put them first in the file, and we put the minor details, the high frequencies that are responsible for fine textures, details of the thin lines, at the end of the file. Because it's just rearrangement, it doesn't cost anything extra in terms of compression. In fact, it makes the compression a little bit better because compression algorithms like to see similar data close together. And that gives you a progressive JPEG. As it starts loading, it loads first the most important background colors, and only later starts downloading finer details. So here's a demo. This is just the first 15% of an image file. It's very blocky, but it's very little data. If we add more data, this is half of the file. And you already see what is in the image with half of the data. It's a low quality. You can notice that it has this characteristic distortion of JPEG. But you get this blockiness in JPEG only if you have not enough data. And the trick with separate blocks and different frequencies breaks down. You start seeing different blocks. So only after we add the rest of the data, the image becomes the final image. But you've seen the last bit of the data barely change the image. Colors change a little bit. It's become a little bit sharper. But while the image is loading on your website with the first few seconds of the site being opened, people will not even have time to look at the image in so much detail. So what you're getting impression of the image being fully loaded with just half of your data for the image. So that's pretty cool. Like you're getting your entire image with half of the data. So why it hasn't taken over the world yet? Why isn't this so fantastic in practice? That turns out, well, it's because on a typical page, you have more than one image. You have lots of images. And when you have lots of image on your page, and each image individually loads progressively, you don't even notice they're progressive. Yep, they're blocky for the first second. But even though now we've loaded half of the data on our page, we still have half of it empty. So those images loaded nicely and smoothly. Each individually seem to load a little bit quicker. But overall, it does not give that wow impression of really progressively loading the page. What we really want is all of the images to load progressively at the same time. Unfortunately, that is very tricky. That's not how the networks work. That's not how the browsers work. Browsers request images one after another and receive them one after another. If we managed to load all of the progressive images in parallel, so that the first progressive layer of every image is now loaded, and then the second progressive layer of every image is downloaded, and so on, it would look like this. Boom. Just 15% of the data for the page here, and it seemed to load in full. So instead of having like 2 or 3 images loaded on the top in full quality, you get impression of your entire site loading almost immediately. Of course, the first layer is kind of blocky, but it's not a big deal. It's going to be followed quickly with the next layer. And on Retina displays, which are becoming standard now, these blocks are half the size, so they're not actually that bad even. So here I'm going to download half of the data of all images. And at this point, they have almost their final quality, their almost final resolution. There's no obvious blocking. And hey, we have all of the images looking like they're loaded with half of the data. If you're looking keenly, you've probably noticed one of the images obviously not loaded in half. It's like half loaded, and this one image is WebP. So it's technically compressed better than all of the other images, but WebP does not support progressive rendering at all. The way the format is constructed, the way it improves the compression, is very clever, but it doesn't allow it to have this progressive feature like in JPEG. JPEG is a much simpler format, so it can simply rearrange the data because each block in the file is independent. In WebP, they're all dependent on each other, so WebP is forced to load top to bottom at its full quality. At this point, unfortunately, it gives very hard to decide trade-off. Do you make your images look loaded faster, but use a little bit more bandwidth, or do you save bandwidth but have images look like they're really slow? Yeah, and now they're loaded. In fact, the JPEGs are still loading. Technically, in terms of file size, the WebP has finished loading on the page first, and the JPEGs continued to load for a second more in this demo. It's just the last bit of JPEG is such a fine detail that unless you zoom in, you won't notice. And the projector is a very forgiving medium. So we can actually implement this, what I've shown you. We can get to load them all progressively in parallel at the same time. And HTTP2 can handle this. HTTP2 supports multiplexing. So even though you have a one connection, the server can chop files into small pieces and send the pieces in any order it wishes. So we can take our images, chop them into small pieces, mix them up, and send them down the wire. To do that, currently you cannot enable a feature in any web server. Nginx doesn't support it. Apache doesn't support it. It's technically possible, but it's not exposed as a user visible feature. So when we cannot get something natively, what do? We hack around it with JavaScript. And here I mean server-side JavaScript. For example, Node.js. Node.js has streams, and streams work in chunks. You as a developer, you're in full control of every chunk of every stream. So you can split your file, your JPEGs, into small pieces and ensure that each piece is sent after pieces of other images. For Node.js, I'm not going to show you exact code for this, simply because it just doesn't fit on a slide. It's not that hard to write, but it requires some bookkeeping that is just hard to present. So I'm going to present the pseudo algorithm. You receive requests. You'll need to set up the raw Node.js create server kind of a request. And usually you serve your static files separately. But for this, of course, you have to do the thing that you don't usually do and direct your static file JPEG request straight to your Node server. And if you send first 500 bytes or so right away, for almost all image formats, that gives you a benefit of sending the header that contains image size. So if you've made the mistake of not specifying your image size in HTML, which of course none of you ever did, it will tell the browser what's the image size, and the browser will be immediately free to start doing CSS and layout of the page without waiting for the rest of the image to load, and without the image to block loading of other resources like your fonts, JavaScript, and everything else you need on your page to start rendering the page. That's a weird hack. Just wait a little bit. Even though browsers conceptually make all the requests at the same time when they request images, they still have to be one after another on the wire. It will still take a moment for the request to be delivered. So it's like a fudge factor. We'll just wait until our server gets to process, gets to see probably other remaining image requests. Then, for every image that we've heard about, we're going to send first 15% of the file. Usually, if you think about, well, we want to serve the first progressive layer of a JPEG, that seems like a complex problem because you need to parse the JPEG, you need to know what's the inside the file and where, and so on. But luckily, all the JPEGs tend to compress very similarly. And for almost every JPEG, first 15% of the file is the nice cutoff where the first progressive layer ends. So instead of doing the complex exact thing, you could just wing it with 15% of the file, and it'll be fine. And here's the complex bit that just requires some clever asynchronous programming and queues and so on. You have to wait for all of your streams from different requests that are running in parallel at the same time to finish sending that first layer. We want all those layers to push out of all buffers to send down the wire to the browser before sending anything else. And this is roughly the algorithm. If you implement this, you will have those nice progressive rendering JPEGs as they should, progressively rendering your whole page at the same time, and making your page look like it's rendered with images with just 50% of your bandwidth. I have a web page test screenshots to prove it. Here's the demo page with just regular images from regular web server, and that's a visual progress of how the page is loaded over time. So as the line goes up over time, it gradually builds the page as image after image loads, as you would expect. It's almost linear. And with the trick, look at this bump. Almost immediately, it jumps to 75% complete. Just as we send those first bits of all the images, the browser lays out the page, starts rendering all of the images, and they're pretty good placeholders. And this is just from rearranging data on the wire. You'll probably heard about different placeholder techniques, low-quality image placeholders, or you can put SVG placeholders or a small GIF file, base64 encoded, and so on. All those tricks and hacks waste extra bytes on the wire, cause your images to sort of be loaded twice, rendered twice. With this rearrangement, we're not wasting a single byte. we're sending what we would send anyway. We're just sending it in the best order possible for our files. One problem with that technique is if you implement it in your own Node.js server, and you're in charge of globally available website, that will probably be a big no-no, because usually you want all your static files, all your images cached on a CDN, so they're available in every city on every continent. But if you try to do it on your single Node.js server and coordinate multiple requests together, you get this global architecture of all the global requests going to your poor server. So until recently, there was no good way around it. You can roll your own, but you don't have a CDN. CDNs don't support that trick. Like, some tried, but they don't. No CDN has released a feature for this yet. The problem looks like this. Even if you implement this on your own server and deliver your images in this beautiful, clever way, this properly chunked progressive unicorn to the CDN is going to save it on its disk in the cache. And when a request comes from the user for this file, it's going to deliver it like a rock. You want your file? Here's your file. And all that effort to serve files properly, it's going to be lost through being saved on a disk cache. But there are edge workers. Edge workers is a new feature at Cloudflare. Edge workers are exactly like service workers, but completely different. Service workers run in the browser. So service worker runs after receiving data from the network, which is still very useful for all kinds of local caching per user or transformation of responses on the fly. But service workers cannot fix this case because all they see is already this huge file as in one chunk. And service workers don't control the network that precisely. But edge worker uses the same API as service worker. So it's JavaScript. It has access to streams. And it runs on the CDN as a filter after taking file from the cache. So even if the image, the static image, the JPEG, gets cached as a single blob of data on the CDN, it's still going to go through the edge worker, where you can control how it's going to be served exactly. So you can implement this super careful splitting of images in the details, in the bits. So here's how roughly it works. It's the same modern web API as service worker. So this would be the handler of fetch event, where you get the full request, the full image. But instead of responding with the image as it is, you insert the transform stream in between. And transform stream gives you, lets you process a chunk coming in and send chunk coming out. And you get to decide what happens with this in between. So we're going to take chunks of data from the response body reader that comes from either cache or your server directly. We're going to use writer from our transform stream to put our chunks in there. The loop that does nothing, just reads and writes back the whole thing, looks like this. And the hack that we can do is roughly structured like this. This is without all the fine coordination between subrequests. When you receive data as a chunk from the origin server, you can, for example, chop the first 500 bytes of it and write it immediately. Then you can add some timeout, or you can wait for other requests running at the same time, and so on. And then chop the array and send the rest of it after that. Exact implementation is left as an exercise for the reader or listener. But this is how you do it. And when you run it in an edge worker, this is automatically going to run in 200 different cities all around the world, straight out of your global cache of your static files. So it's going to be super fast and delivered properly. So that's the cool thing that you can do yourself. I've just recently proved the concept, so I don't have a ready code for you yet to download and install. If you write it, then I'll happily just take it. And to create nice progressive JPEGs, still the best solution for JPEGs is MozJPEG. It's an open source library written by Mozilla. It's not your old JPEG. It's compatible with your old JPEG, so it works in all browsers without any problems. But it compresses better. It automatically uses all the right settings that you should use when generating your JPEGs. And they're always progressive. If you're on a Mac, you can just drop your JPEGs into ImageOptim, which is my application, and it has MozJPEG built in. If you want to run it on your server, there are tools, libraries, services to choose from. You'll have to find the best way to integrate with your system. So that's been the JPEG. We still can squeeze so much from JPEG and make it appear so fast. But whenever I talk about JPEG, the next question that comes up is like, but what about with WebP? We don't have many image formats in the browsers, and apart from the very, very old ones, like JPEG is from Spec is from '92. The library that everyone uses is from 1998. Like those are really old formats. So whatever new we get, it's like seems like a really hot thing. But actually, everything we have available is kind of old. So it goes like this. WebP has been invented as a quick hack when Google bought and released a VP8 codec. At that time, the web did not have any good free codec. Those were the dark times of Flash and YouTube having the small pixelated window with barely got rid of other horrible video plugins. So at that time, when Google released the free, open source, royalty-free codec for everyone, that was great. Like we thought, it's gonna take over the world. Why wouldn't you use a thing that is nice, modern, and free? And given the prospect of everyone is gonna using this new VP8 video, why don't we also get an image format for free? So every WebP image is actually a single frame of WebM video. It uses the same library, the same compression technique. It's based on the assumption like if everyone's gonna be decoding the WebM videos, they can as well decode WebM-like images without adding extra code. But WebM in the VP8 form did not take over the world. It got soon replaced by either the proprietary H.264, which is to these days probably the still most popular format, or a newer version, VP9, that's currently used by YouTube whenever possible and used for 4K videos on YouTube. So VP9 is a significant improvement over the VP8 technology. VP8, even though WebP was released in 2010, VP8 was developed in 2008 and lost in the market to a codec from 2003. So it's like the VP8 is kind of old by now. The video world moved to VP9. We didn't get a VP10 release because we've got even newer, cooler stuff. Mozilla, in the meantime, was working on the new DALA codec. Cisco was working on their new video conferencing codec called Thor, and Google was working on VP10, VP11. Unfortunately, they all got together and thought, like, why don't we work together? Why do we need 3 different codecs? Why don't we develop one that is pretty good? And they did. It's called AV1. All those browser vendors together and other vendors created Alliance of Open Media. And very interestingly, for the first time, Apple is on board in that alliance. Before, Apple was like on the top H.265 H.265 track, and iOS devices currently use H.265 behind the scenes. So on the latest iOS, when all the photos you take are probably already moved from JPEG to H.265, and H.265 is a very good codec. It's half size. Both H.265 and AV1 are half size of everything else that came before them. AV1 has shipped in Chrome 70. It's ready to ship in Firefox soon-ish, and it's half size of WebP. It's a video codec. So there's this trick. We have a video codec that is very efficient, would like to use it, but it's not an image codec. But WebP is an image that uses video codec. So why don't we hack it? So here's a very unfortunate hack. The best way today to compress an image in the browser is to use a video tag. Don't go overboard with this, because when you embed a video tag, browser thinks you're really, really serious about playing video, and it's going to allocate memory, it's going to spam background threads, and it's going to do weird things with GPU. So if you put 50 of these on a page, Chrome is going to really, really hate you. But that's the way currently to get the AV1 codec, which is half size of WebP. You can use FFmpeg. FFmpeg 4.0 has shipped with support for this built-in. So if you install latest FFmpeg, you can convert an image into one frame of AV1 and embed it in a video flag with muted. That's necessarily to display without any ceremony. Autoplay, so it's actually shown, and plays in line to tell Safari not to show it on a full screen, because that would be weird if any of your avatar images suddenly popped up to the full screen. So like I've mentioned, this is a hack. This is a hack. If you're in a desperate situation where your design director tells you, we really, really have to have this hero image that's like 4K resolution with somebody smiling to a salad, and they've given you a JPEG that takes 5 megs, then you can make it 2.5 meg AV1. So this has been my last hack for today. But don't focus on the video hack. Focus on the progressive images. That's where that's what you can deploy today and have a huge improvement. You can even losslessly convert all your existing JPEGs using most JPEGs JPEG Tran pool. So you don't lose any quality on conversion. They'll become progressive. They'll compress about 15% better or more, depending on how bad the software was that you've used to create them in the first place. And then in the meantime, we're hoping that AV1 will become usable for images in the browsers. There's already sort of a vague spec for WebP-like version of AV1. I cannot tell when it's going to actually ship. So until then, that's what we have today. Thank you very much.
Right, great talk. I always come to these and think everybody else is just so much cleverer than I am, and Kornel is certainly one of those people. Right, while Michael's gone to get the pizzas, any questions for Kornel while we set them out? Right, first at the back.
So I assume the idea might work on Edge, Lambda Edge or something like that as well. Or
Probably not, because Lambda itself might be behind several layers of other networking proxies. I haven't tested, maybe.
Okay.
I assumed it might not be too fine-grained enough and low latency enough to be worthwhile to use with static files.
But you're using cloud workers.
Edge workers, yes. Edge workers. I think edge workers have lower latency.
Sorry, did you say you were giving this talk at Cloudflare yesterday? Or was that the second talk that was given at Cloudflare yesterday?
This talk was first presented at Perf Now in Amsterdam last month.
Okay. Well, the follow-up question to that then is, will Cloudflare be bringing this out as a product?
There's my manager.
Lovely. Thank you very much. Is he going to wave? Yes. Thank you very much.
There you go.
Is that a yes?
That was a yes. That was a yes. Yeah, now I have to write it. There you go. All right, it's pizza time. Thank you.